So we finished hashes, and now we are into the next step, which is how to use those hashes for message authentication. And in this part, we will talk about the common methods. First of all, what is message authentication, and then three methods: HMAC, CMAC, and GCM. Actually, those are the three. And then we finish with pseudo-random number generation using hash functions and max. So when we send a message, we want to protect it from many different kinds of things. First of all, we don't want to disclose it, and that may be optional in some sense that sometimes the message could be public. So all of these are not required. These are things that we may want. Traffic analysis, that we don't want anybody to know that I sent a message, because particularly in the defense arena, it is important to know whether United States sent a message to Iraq, Pakistan, this and that, and so nobody should know even the count of the messages. Traffic analysis. Masquerade means somebody else cannot become you. Content modification, so nobody should be able to change the content. Sequence modification, they should not be able to move the messages around so that second message becomes first. Timing modification, so that they could not pay the message tomorrow instead of today. Replay attacks. Source repudiation, that this is important, is that we want to make sure that the source cannot go back on its word. So if the source sends you some message, they cannot say, well, I didn't send that message. Right? So that's where we get into signature kind of stuff. And then destination repudiation, and destination cannot say that it didn't, it was not, basically destination was changed, something like that. Alright? So the authentication actually is not very well defined, but one definition of authentication is integrity plus source authentication. So we are sure that it came from that source, and we are sure that the method has not been modified. And you can add any of these fields in that integrity thing. Now, if you want to make sure that the timing is correct, you put the time inside the message and then protect it with this, whatever integrity check there is. If you want to protect sequence, obviously you will put the sequence number inside, inside the protected part, and so on and so forth. So putting the source alone does not help that. So basically we need to have something that only source knows, because if we just put the source address and we protect it, that is a very, very not valid proof, because somebody could say anybody can put that source address. Right? So the message had that source address, that is proven, but that doesn't mean that I sent it. Alright, so we have to make sure that in addition to the source being protected, somehow we can prove that the source sent it. And we already talked about one of these methods. When we were talking about the public key and private key, this picture is taken from that slide, is that we take a message, take the A's private key and encrypt it, then we take the B's public key and encrypt it, and then we send the message. And then B can be sure that only A could have done this. Right? The only reason this is not really done in practice is that we cannot really handle full messages with public key. Public key methods are very compute intensive. If you can handle 64-bit, that is big enough. You cannot handle 500, large messages. So we really don't apply public key. Public key method is used only to encrypt the keys, encrypt the secret keys, because those are small numbers, and then we send it to the other side in public, and then we can use the secret key. Alright? So this method, while theoretically it will work, practically it is not used. Instead, what we do is we get a hash or a checksum or something, and that can be used with any kind of public key stuff, or any other kind of thing. So So what we do is we do a crypto checksum. So we do and checksum could be called a hash as well. So we do a crypto checksum, and here K is a secret, and then we concatenate it to the message. So we send the message. Now here, as shown, the message is being sent in clear, but it's trivial to just encrypt it, if you want to encrypt it. So that's optional. That has nothing to do with the message authentication. And your message sent in the clear, and this thing which came out here is put here. So that's basically concatenated. At the end of the message, you have this called message authentication code, MAC. So the receiver can do the same checksum using the same key and compare that it gets the same checksum as it was came here. Right? If there is no secret key, then this would be simply message digest like MD5. We talked about that last time. We just use MD5 hash to protect the files. There is no secret. Anybody can calculate MD5 hash. But in this case, if we want some kind of secrecy, so that we want to ensure that nobody else. The problem with that, without the secret, is that anybody can modify the message and the checksum. So we don't want anybody else to be able to modify the checksum, and therefore we have to have a secret. So this is a common method. Now we didn't say whether this is public or private or what it is, and so there are many variations of this. So the MAC is a cryptographic checksum which uses a key K, and it condenses a variable length message using a secret key to a fixed size authenticator. So basically it is like a hash with a key. It's a many-to-one function, just like a hash. It's a many-to-many function. So many messages can have the same MAC, but finding these messages is very difficult. So like a hash, it is one-way function. You can give it a message, you can calculate the MAC, but given the MAC, you cannot calculate the message. So therefore it is infeasible to find another message with the same MAC, obviously, and MACs should be uniformly distributed, so they are totally random, and MACs should depend equally on all bits of the message. That means if any bit is changed, the MAC should change significantly, which is obviously then only it will be authentication, because if we change few bits here and there and the MAC doesn't change, that basically allow people to change the message without getting caught. So just like the hash, MACs can be broken by brute force attacks, but if you have an m-bit MAC, you would need 2 raised to m by 2. Anybody remembers why 2 raised to m by 2? Why only half the bits? There was some kind of paradox. Anybody remember the paradox? Birthday paradox. So basically, if you have 365 days in the birthday, you only need the square root of 365 number of people to find 2 people with the same birthday. Similarly, if you have m-bit hash, m-bit MAC, you only need square root of 2 raised to m, which is 2 raised to m by 2 attempts to find a colliding message. So MACs with known message and MAC pairs. So if you get lots of these pairs, then you can do the key search. And so basically, because of 2 raised to m by 2, 128 bit hash today look vulnerable, means you generally will not use it. 160 bit is here right now, but as the time go by, we will probably move to higher size hashes. Now, anybody remembers where 160 comes from? What is 160 bits? Is there some particular program or algorithm that gives you 160 bits? Do you remember any hash and remember how many bits it gives you? SHA-1 gives you 160. right? Yeah. So that's the most common hash, and so that's what minimum you will use today. So one of the standards for message authentication code is HMAC. So this is a standard. Actually, it's not really a complete, it's more of what we call, I am not getting the word, but basically it's a design rather than an algorithm, because you can add any hash function along with this design. It's like Feistel structure. Feistel structure can be used with many different mangling functions and so on and so forth, right? Similarly, HMAC is a structure that you can use with any hash function. For example, you can use with MD5 and that will be called HMAC MD5. You can use with AES and that will be called HMAC AES. You can use it with SHA, whatever, and you can call it HMAC that. Okay? So it can be used with any hash function. And you use those hash functions without modifications. We don't change anything to the hash function, we just put them in this design, which is coming up. And therefore, you can easily replace the embedded hash functions. So as the hash functions become less and less secure, for example, MD2, MD3, MD4 we no longer use. MD5 is probably not going to be used too much in the real secure world. So you can still use HMAC. All you do is just replace MD5 with SHA-1 and then later on with SHA-2 and with SHA-3 and so on and so forth. So you can replace that little module in this design. And it uses handles and keys in a simple way, has well understood cryptographic analysis for authentication and maximum strength. So the good thing is that people have analyzed it, and so this structure is good. So what is the structure? The structure is specified in RFC 2104. How many people know how to get RFC 2104? Nobody in the class knows how to get RFC 2104? Do you know how to get RFC 2104 on the net? Yeah.
Oh, yeah.
How do you get? Google RFC 2104. Anybody else knows better than that? IETF.org. That's the answer. So basically, if you go to IETF.org, they have all the RFCs. And those of us who work in networking area, we keep it on my computer. I have all these 5,000 RFCs on my computer, so I can look it up right away. Obviously, you can Google anything and you can find it. that's but the real source Google finds it is from IETF. And so all the requests for comments are there. And so this is one of the networking RFCs. And so this is the structure. So let me explain slowly how this structure works. You take your message, which is Y through this one. This is your message. And you put something in front of it. And then you hash the whole thing. And then you put something in front of the hash. And then you hash it again. So you hash it twice. So if you were doing MD5, you will do MD5 here and MD5 here. Right? You use that module twice. Now, first of all, the question is, what do you do? So, because most of the hashes require you to break the message into blocks. For example, SHA-1 might require you to do 512 bits at a time. Even though it produces 160 bits, but it takes 512 bits, right? So that is the B bits. So 512 bits, 512 bits, and so on and so forth. You break the message, right? And you are going to give one block at a time into this hash thing. But what you put in front of it is this thing which is an exclusive OR of two numbers, K plus and iPad. Okay? So K plus and iPad. What is K plus? K plus is a key that you have selected. This is where the secret comes in. This is your secret key, and you pad it to B bits, because the key may not be 512 bit long. Your key might be 160 bit long. So you make it 512 bits, padded to B bits. R hash to B bits if K is greater than B. Suppose your key is 1024 bit long, then you compress it to 512 bit. And that compression doesn't have to be the same this MD5 hash. That is totally independent. So somehow you make the key whatever it is to the size required by your hash, this hash, by expanding or compressing. Then IPAD is a fixed constant. IPAD is number 36 repeated B by 8 times. B is the number of bits, 512. B by 8 is B by 8. 512 times divided by 8 is 64. 64 times 8 is 512. So 64 bytes of 36363636363636. So that power is, you have to remember, this is not a power, it's just a repetition. So 36 is hex. So you write down 011 0011 and then 0110, that is 36, and then you just repeat that bit pattern. So you take that iPad and you take the key and you exclusive R. So basically what you are doing is you are not using all the bits of the key. Some bits here are 0, that is where the key will pass. Where the bits are 1, the bits will be complemented, so you get something different. And then you put it in front of M, which you already did here. This is the thing you put in front of the message. You hash the whole thing. You hash the whole thing, and then you get this 160-bit hash. All right, this is the 160-bit hash. If this is SHA-1, this will be 160-bit hash of S input and the message. Now you take the same key and exclusive R it with OPAD. And the OPAD is the number 5C repeated 64 times. So 5C is a different bit pattern than 36. It turns out basically if you write down 36 and 5C, they use some bits, very few bits in common, but they have different set of bits. So you use a different set of bits here, and then you put that here S0 in front of it, and you hash it again, and you get this thing which is HMAC. All right. So this is what is called HMAC. So HMAC is not one algorithm, it could be any algorithm. If you use MD5, it is HMAC MD5. If you use SHA-1, it is HMAC SHA-1. If you use RIPE EMD, whatever that is, RIPE EMD, Whirlpool, these are all different hash functions. And so you can use that with HMAC. This is the HMAC structure. So somebody did this analysis in the crypto world, and they said that if you use this kind of a structure where there is a key in the front and there is a key here second time, then people cannot muck around with this message authentication code. This is very secure, and this is the best way, and it has not been broken, so people are still using this same HMAC. Only thing which will change with time is the hash function. All right. So this is also called a keyed hash because you are using a key. The IV is basically could be a fixed number like all zeros or something like that, and so that the receiver, only thing they need to know is the key. And these numbers are constant. So 36 and 5C, the whole world uses those two numbers. Alright, so iPad and OPAD are constants. And K plus is basically the key compressed to B bits. And you understand the difference between B and N. B is 512 for SHA-1, N is 160 for SHA-1. Right? B is the message block size and N is the hash size. Right? And obviously when they selected these constant, a lot of analysis would have gone behind it. They would have tried out all 256 possible values and maybe all possible combinations of 256 values, and then they said, well, these two, give the highest level of security, whatever. So those numbers are still used same way, 5C and 36. So the next question is, are these steps clear, or is there any question about any of these steps? George, makes sense a little bit? Now this is HMAC. So you can, so that is one way to use hash. Another way is to use ciphers, symmetric ciphers. So you can use, for example, DES, DES or AES. Both of them are symmetric. Those are both of those are secret key encryption schemes. So you can use that, and you use that in a cipher block chaining mode, which means that you take the cipher block and then chain it to the next line, next block, and next block, and next block. This is your message. This is your message, and this is the first basically block of the message. You encrypt it, you get the output, you feed it to the next one, and so the last one is your hash. That's it. So when you want to send the hash, you don't send the whole thing, you just send the last one. So this is called data authentication algorithm, DAA, and this is basically DES with CBC. Everybody knows what CBC is. Cipher block chaining. Cipher block chaining, CBC, and that is what means this. Okay, and DES is right here. This will take 56-bit key and 64-bit message, 64-bit block, and produce 64-bit output. So the final hash would be 64-bit long. Now you don't have to, by the way, okay, that's another point I forgot to mention, that you don't have to use the all 64-bit. You could say I want to have a 16-bit hash, and you could just take the first 16 bits, and that would be a hash as well, right? It will be weaker hash. But not only the less than 64 would be weaker, even 64-bit is not very strong. I mean, because it will take only 2⁻32 attempts to break it. So this is not something that you will use, but this is a possibility. Now there is a clear break in this security, is that if you just have one block in the message, just one block, so there is no chaining. If there is no chaining, then your hash will be equal to K and X. This is X is your message and K is the key, and so whatever is the encryption of K, encryption of X with key K is your hash. Right? Now if somebody modifies this message X to X concatenated with X plus T, X followed by X plus T. So let's see what is that. That is a 2-block message. The first block is X. The second block is X plus T. T is this thing. Right? So what will happen? You take x plus t and the t comes from here, you add that, what will you get? After exclusive OR, what will you get? When you exclusive OR x plus t with t, what will you get? Anybody knows what will you get on this line here? I sent a one block message x, but somebody made a two block message out of it. The first block is x, the second block is x plus t. Now the receiver is trying to check out the hash. So they run the x and they get a t here, and then they feed the t back here, so and then they add it to x plus t. You get x, exactly. So here you get x, so what do you get here? T, right? So now what has happened is, now we have a two block message which has the same hash as the one block message. The sender sent a one block message and the receiver received a two block message with the same hash, and it's very trivial. All the attacker has to do is to exclusive OR the hash with the message and append it. Right? So this is not good and we need to fix it. And so the fix is called, actually there are two ways to fix it which will come up later on, but let's first introduce CMAC. So basically, I mean, CMAC is one of the fix which was proposed by these two guys, Black and Rogaway. They fixed that problem that we talked about by using three keys. They said instead of just one key that we had here, use three different keys. And so you use a key here, then you use another key here at the end, K1, and then when you, if the message is integer multiple of the block size, so if there is no padding, then you use K1. If there is a padding, then you use K2. So there are three keys, K, K1 and K2. If you do that, then nobody can play with adding by adding one block. All right. Then somebody else came up and said, no, you don't need three keys. You can generate the other two keys from one key. So you can just use one key and then, you know, do something with that key to get K1 and K2. And so that is what was adopted by NIST, and that is called CMAC. CMAC is the NIST standard SP 800-38B, and in that standard basically what you do is you derive two n-bit keys from a k-bit encryption key. Two n-bit keys from a k-bit encryption key. So to get that, what you do is you first generate L, which is the encryption of k with 0 n zeros. Basically 0 raised to n means you write down 0 n times. So you encrypt the key k, so now you get some random number L. Then you multiply it with x in Galois field 2 raised to n using this polynomial. Okay, so all of you should now know how to do multiplication in Galois field 2 raised to n. There are two choices, I mean basically of Galois fields. Either you use Galois field with prime numbers, in which case you don't need the polynomial, the life is much easier, and that is good for software implementation. Another one is Galois field in 2 powers of 2, in which you need the polynomial, and this is good for hardware implementation. Right? So here they are using Galois field 2 raised to n with this polynomial, and all you are doing is taking this L as a polynomial, multiplying it by x, that is your first key, taking the second polynomial, multiplying by x squared, that is your second key. Now when you multiply, generally nothing will happen except it will be shift left. When shift multiply by x, yeah, you just all the powers will go up by 1, except that there might be an overflow, right? If it becomes L raised to x raised to 64, then you have to subtract this quantity, right? Similarly, if you are using 128 bit, then you use this polynomial, and then so only if the last bit becomes, if the most significant bit becomes 1, then you have to subtract this quantity. All right. So I suppose it is clear to everybody how to do CMAC then. For CMAC, if you have to do CMAC, you have to derive two new keys, K1 and K2, using this Galois field multiplication from K. And depending upon whether you did have to pad or not, you use K1 or K2, only one of the two. And whatever you get at the end, you take whatever number of bits you need to get your MAC or hash. Is that, so this is T length, most significant T length. So that is the length of your hash. You don't have to take all 160 bits or 128 bit or 64 bit. You could take whatever number you need from the front. Okay. It turns out the more you go towards the front, the more random the bits are. Not all bits are equally random. Bits at the other end are much more predictable. So you always take it from the front. Most significant bits, T length. Alright, so this is CMAC. So now we learned about two different MACs, HMAC and CMAC. So the next issue is, what if we want to encrypt? In addition to integrity, we also want to get confidentiality. So far in the MACs, we sent the message in the clear, and only thing we sent was this MAC. Now we want to encrypt the message also. So there are four possibilities. First, you could hash. So take the message, hash it, concatenate the two, and then encrypt it. Or you could do the, instead of hash, you could do MAC with one key and encryption with other key. Or you could encrypt it with one key and do MAC with other key. But when you do the MAC, you take the ciphertext from here. So this will be encrypt, then MAC. Our fourth method is that you encrypt and MAC in parallel. So you are doing the ciphertext here and you are doing the hash here. These are two different keys, and you can do that in parallel. The ciphertext is not used here. All right. And so all of these have advantages and disadvantages, and different solutions have taken different ones. For example, SSL and TLS, which are used on the web, they use this one. IPsec uses that one. SSH uses that one. Okay, and all of these have little bit of some problems, and so NIST suggested two algorithms called CCM and GCM to fix those problems. CCM is counter with cipher blockchaining, and this is used in Wi-Fi. And the way it works is that you take a counter, this is your counter, so this is counter mode like we used before. You encrypt the counter and then you exclusive OR with the message to get the ciphertext. And the only thing is that this is your message. To the message you add something. This is your message is P1 through PM is your message, and you add to it the tag that you calculated before. So the way you calculate the tag is that you take your plain text and you put something in front of it, and then you run the whole thing through the MAC algorithm with a key, and you get the tag. Okay, so what do you put in front of it? In front of it, you put a random number, nonce. Now, nonce means not used again. And so that is a random number you put, and then you put some associated data, something else that you want to protect. So, for example, even though the source address is going in clear, you want to make sure nobody else modifies it, so you put it inside the packet as well. Right? So you might have something more than the message. So this is associated data, means some other fields in the packet that you want to protect. Right? So you put all those things, and then you break it down into the blocks and run the CMAC with a key, and you get the tag. That tag is used here. Okay? So let's see. So you use AES encryption algorithm. So this is AES. You use CTR mode of operation. This is CTR right here. And you use CMAC authentication, which is right here, CMAC. And a single key is used. The same key is used here and here for both encryption and MAC. And two passes. The only problem with this algorithm is that you have to make two passes over the plain text, one for the MAC and then one for the encryption. And this is basically, if you have to go back to the previous four possibilities, can anybody guess what sequence is this? So there were MAC and encryption, M and E, right? So which one is first? Huh? MAC is first, because if you don't do tag, you cannot put it here, right? So this will be M, then E. So MTE. Oh, I should not have said that. But anyway, so this was the homework. All right. So the next one is GCM. And here, this is another one of the standards. The advantage is this is parallelizable. Here you could not parallelize it because these counters are related and so on and so forth. So this is parallelizable, and you use two functions. One is called G hash and one is called GCTR. This is the G hash function, and this is the GCTR function. So this is very similar to, G hash is very similar to CBC kind of thing. You take your message, you take a key and you run through H. Whatever you get, you take to the next block and then next block and next block, and at the end you get YM, that is your hash. And G hash is actually this, when I say you have to hash it, that's actually a multiplication with the key in Galois field 2 raised to 128. And so there is a polynomial which I have not put here, but there is a 128 power polynomial that you will need to do this multiplication. And that will give just the hash. And if you don't want to do the encryption, you don't have to do the second part. You can just do the hash and you're done. So then what you do is, for the message, you take your message and you take some initial value and then you generate the you use the key to generate the encryption, and you can exclusive or your message to get these values. At the end, you take the most significant bit of the last block, to which you add x star n, and we'll talk about that in a minute. This is your x n minus 1, this is x star n, and that gives you y star n. Now, so this is y star n is basically the function of the whole thing, initial value, and then you have all these xn's to xn star. The key is to confuse. I have whited out here. In the book, it says y1, y2, y3, ym. And then in the bottom it says y1, y2, y3, ym. And they have nothing to do with each other. Right? So again, I have problems with the symbols throughout this book. And this is one of the problems. You can't use in one figure same symbol for two different meanings. Right? So in this figure, if you look in the book, there is some text here which I have deleted. So basically ym I have left because there is no ym in the bottom. But basically, so that's it. The y is on the top and y in the bottoms are totally different. This is the result of the AES encryption. This is the result of this multiplication. All right. So let's summarize this GCM method. In GCM method, we use a Galois field multiplication to get the hash, and we use this almost like a counter mode AES encryption to encrypt. All right, and let's see, the only detail I have not put here, and somehow I forgot to put it on this slide, is xn star. And xn star basically has to do with what to do with the last block. If it is partial, then how do you do the padding? So the details are not here. But you have to send both ym and yn star. All right. So now that finishes the two authenticated encryption algorithms. So let me summarize again. First, we talked about two different MACs. One was called HMAC, then other one was called CMAC. Then we said, well, in addition to MAC, what if you want to have confidentiality? Then there are 4 methods, and therefore the NIST specified 2 standard methods, and they are called CCM and GCM. CCM, as you can see, uses basically creates a hash and then puts it into a counter mode encryption, and GCM uses a hash which is based upon Galois field and puts basically in parallel, so it doesn't really put it in one to the other. All right. So that finishes that part. Now we are in the whole last part of this whole chapter, last section of this chapter, and this is how do you generate random numbers, and that should be trivial by now. We have generated so many random numbers that using hash and max is not a very big deal. All you need to do is get a seed value and then you run through the hash. Keep running through the hash and you keep getting the random numbers, or keep running through the max, keep getting the random numbers. So all you need to do is seed value, and seed must be known only as needed. So as long as people don't know the seed, they can't generate the same random sequence, and they cannot decrypt, encrypt, or do anything with that thing, right? So the PRNG can be based upon the encryption algorithm, can be based upon the hash function, can be based upon the MAC, and all of these are exactly same. And for the hash function, you take any value and get the output. Now your one possibility could have been that you can feed back the same output input and get the new value and new value, or another one is that you just keep changing the I by 1. So you have some value of v and then v plus 1, v plus 2, and then you keep getting a new number. With a MAC, similar possibilities exist. You take a v value and then you feed it back, or you could also have done with plus, but somehow the standard specifies that you do this cipher block chaining kind of thing. Feed it back. So that brings us to the end of this chapter, message authentication code, and here are the 6 key points. First is authentication means integrity and source authentication. Encryption is not part of it. Encryption is just you can do with or without encryption. So that's totally orthogonal decision. Authentication simply means that the message has not been modified and that the source is correct. Double public key encryption can be used, but it is complex and therefore we don't use that at all. We use hashing with a secret key. This is called a keyed hash. HMAC is a procedure, general procedure which you can use with any function. So we now know that HMAC is alone itself is not really meaningful. You have to say I am using HMAC with MD5 or I am using HMAC with AES. HMAC is just a structure. Fourth point is that DAA was not secure because anybody could make 2 block messages for any given 1 block message. Right? You give me a 1 block message with a MAC and I can create 2 block message by exclusive ORing the MAC with the message and it will have the same MAC. Right? So that was trivial to break and therefore they fixed it using CMAC. And then if you want to do encryption in addition to authentication, then you have 2 choices, CCM and GCM. CCM uses CMAC and a counter mode, and GCM uses multiplication and a counter mode. Then you want to do pseudo-random number generation. There are 2 methods. Either you can increase the counter and keep hashing it, or you can feed back the cipher value and keep hashing it. Now the homework 2.12 is kind of trivial homework. You just have to see which method is used in CCM and GCM. I already told you the answer for CCM. So now the next thing is what is for GCM. So you have at least half of the things to think about. Any question about this? So actually, I mean, like we finished it fast, but this is actually a topic that doesn't really deserve a whole chapter. Last time we had 4 or 5 slides on MAC in the last offering of this course, but this book has a whole chapter on it, so we put a whole chapter, but it's not a very long chapter. Any question about any of these MACs or anything? In particular, make sure that you understand all these 6 points, because I try to put on the summary slide the key things that are important to learn in this whole chapter. If some of these is not clear to you, if some of the words don't make sense or some of the conclusions don't make sense, maybe you should ask now.